Hi, I'm Mr. Miller, and this is a lesson on characteristics of exponential functions. So exponential functions are like this. They're functions of the form y equals c to the x, where c is a positive constant and x is a variable. So with that form, you can get one of two situations. Either a graph that looks like this, and that'll be the case when the base, that constant c, is greater than 1, you'll have an increasing function. Or you'll have something that looks like this, and that's the case when c is less than 1. Keep in mind c is positive, so it's going to be greater than 0. So basically what we're saying here is that in this case, if c is something like a fraction, like a half, a third, a quarter, or a decimal that's less than 1, something like 0.9, then you will have a decreasing function. If c is greater than 1, so even just 1.1, or 1 2/3, or 5, or anything that's greater than 1, you'll have an increasing function. So let's look at a couple of specific examples. So we're starting with the graph of y equals 2 to the x and the graph of y equals a half to the x. We're going to do that on the same grid below. And for each of the functions, we're going to identify a bunch of characteristics. So let's take a look at how we would do this. Whenever you're doing a graph of a new function, it's handy to do a table of values. So here are a few easy x values for which we can calculate the y values, and then we'll be able to plot them on the graph. So you should know these powers. 2 to the 1 is 2, 2 squared is 4, and 2 cubed is 8. Now, it's not unusual for people to get confused over 2 to the 0, so let me just talk about this for a minute. When you're going down each one of these steps, you notice that you're dividing out a factor of 2. So if I continue one more step and divide by 2, that will tell me what 2 to the 0 is. In other words, 2 divided by 2 gives you 1, and that's what 2 to the 0 is. And you can continue that pattern along and divide by 2 again to figure out what 2 to the negative 1 would be, which of course would be a half. And if you divide by 2 again, that would give you a quarter, and divide by 2 again, that would give you 1/8. So now that we've got these points figured out, we can plot them on the grid. And you can see the trend here, which is as x gets large, y is going way, way up. And you can imagine we've figured out 2 to the 3 is 8. Of course, 2 to the 4 would be 16, so it's way up here. You can see the direction that's going. On the other side, as x is getting negative, you can see we're getting closer and closer to 0. So I'm going to fill in with a curve that matches that description. And I'm going to put arrows on the end to show that the relationship continues on in both directions. And now I'm going to label that y equals 2 to the x, because of course now we're going to be doing y equals a half to the x, and we want to be able to have a label to distinguish which one is which. So now let's do a table of values for y equals a half to the x. So I'm going to start with the same set of x values and calculate the y's. So I'm going to start with a half to the 1, which of course is a half, and a half squared would be 1/4, and a half cubed would be 1/8. Now, similarly to what we did here, notice we were dividing out a factor of 2 each time we were going down here. When we go down each step here, we're dividing out a factor of a half. Now, dividing out a factor of a half is equivalent to multiplying by 2. So notice that 1/8 times 2 is 1/4, and 1/4 times 2 is a half. So if we multiply by 2 again, that will help you to figure out what a half to the 0 is, which again, this is the kind of thing that maybe people forget. What is the rule for when we have a base raised to the exponent 0? And provided that base isn't 0 itself, the answer is always going to be 1. And this patterning just helps you to remember how to get to that. And if we continue along like that and multiply by 2 again, 1 times 2 is 2, and multiplying by 2 again, we get 4. Multiplying by 2 again, we get 8. So we can take all of those points and plot them on the graph, and you can see the trend that's happening here, that as x goes to large positive numbers, it's going towards 0, and as x goes towards negative large values, it's going up towards infinity. So I'm going to fill it in with the shape of the graph, put arrows on both ends, and I'm going to put a label on it, y equals a half to the x, which I'm saying is the same thing as 2 to the negative x. So for those of you who haven't put the connection together yet, 1/2 is 2 to the minus 1. So if you have 2 to the minus 1 to the x, what you do with the -1 and the x is you multiply those two exponents, and this becomes the overall exponent is -x. So we've got 2 to the x and 2 to the -x. These are the two functions. Now let's take a look at some of those characteristics. The first question was about domain and range. Well, the domain of both is real. So there's no restrictions on what x can be for either one of these functions. It can go from positive infinity to negative infinity, and it can even be 0. The range of both is y is real, but y is greater than 0. Notice I'm saying y is greater than 0, not equal to 0, because although both of these get really, really close to 0, they never quite touch. Neither one of these has an x-intercept. As I mentioned, they get really close to 0, but they never quite touch the x-axis. So that means they don't have x-intercepts. But they both have the same y-intercept. You notice they both cross over at 0, 1. Y equals 2 to the x is increasing, and y equals a half to the x is decreasing. And the rule for increasing or decreasing is if you trace along the graph going from the left end of it to the right end of it, the direction, you can see it's going up, so that's increasing. So that's for y equals 2 to the x. Now if I go over to y equals a half to the x, or y equals 2 to the -x, as we go from left to right along the graph, you can see that the y values are decreasing. The equation of the horizontal asymptote of both is y equals 0. And you might be wondering, why did I change colors? Well, it's because I wanted to highlight this is the horizontal asymptote here, and it's y equals 0 is the equation of that. So let's move on to another example. Now we're given a graph and we're being asked to determine what is the base here, which we're using the letter C for that variable. We notice that this is increasing, which means that C must be greater than 1. And the point that we want to look at in particular is when x is equal to 1, what is y equal to? So I know it's a little bit small, but I'll read that off for you. It's y equals 3. So that 0.13 means when x is 1, y is 3. So this gives away what c is equal to. C is equal to 3. And so the equation for this graph is y equals 3 to the x. Next, we're going to take a look at this example with bunnies, otherwise known as rabbits. And we've got a population of rabbits that's initially 10 and it doubles every 3 months. We want to make a table of values to show the population over the first 15 months. We also want to graph this data and find the equation which describes this population growth. So let's get into that. Here's the table. I'm going to use T for the time in months and P for the population, which is the number of rabbits. And you notice that I'm going T equals 0, 3, 6, 9, 12, 15. I'm going up by 3s, and the reason for that is because this is when the population is doubling every 3 months. So now I can start with the initial population, which is 10, and I can double that to 20, and double it to 40, and 80, and 160, and 320, and now I've filled my table. Now before I go on, what I'd like to do is just do a little bit of analysis. You notice that this 10 is 10 times, now this might seem strange. Why did I write times 2 to the 0? Well, first of all, 2 to the 0 is 1, so I haven't changed the value of this. It's 10 times 1 is 10. But the reason that I've written it in this form, times 2 to the 0, is because all of these populations can be written in this way. The initial number of rabbits, 10, times some power of 2, and 20 is 10 times 2, which is 2 to the 1. 40 is 10 times 2 squared. 80 is 10 times 2 cubed. 160 is 10 times 2 to the 4, and 320 is 10 times 2 to the 5. So all of these population values follow this rule. It's the initial population times a power of 2, and it's raised to the exponent, which is not exactly the number of months, but it's the number of 3 months periods that have gone by. Notice that? Okay, so let's take a look at doing a graph here. Now, what I've done is I've set up my grid to go from 0 up to 18 months, because looking ahead to the last question we're going to answer, we want to know when the population is going to reach 600. And we know that after 15 months the population is 320, so it's probably going to take close to 18 months to get up to that 600. 2 times 320 is 640, so I'm just leaving some room at the top for that. And I'm also leaving some room here to go up to 18 months. So now that I've got my points plotted, I'm going to just put that last point, 640, although it wasn't in the table. I know that we want to see approximately when the population gets to 600, so I'm just putting one more point beyond what was in the table here, and now I'm going to graph this. And so now this is the equation for that function. It's p equals 10 times 2 to the t over 3. So this looks a lot like what I have here, 10 times 2 to the power of. And the reason I've written the exponent as t over 3 is because we have to take the time and divide it by 3. Now that doesn't do anything for 0, 0 is just 0. But 3 divided by 3 is 1. 6 divided by 3 is 2. 9 divided by 3 is 3. So we're dividing by 3 because this is the amount of time, 3 months, for the population to double. So now I can use this to do some things like figure out what is the population going to be in 10 months, which isn't in our table. But we know it's going to be somewhere between 80 and 160. It's probably going to be, maybe it's going to be a little bit closer to 80 than 160 because it's only a third of the way, but we can't just do a linear extrapolation. This is a curve, so we're going to have to use this equation to work that out. So let's do that. 10 times 2 to the 10 over 3. And if you put that into your calculator, you got to be really careful. Put the 10 over 3 in brackets. Otherwise, you might end up doing 10 times 2 to the 10, and then just divide that whole expression by 3. You should be getting an answer of 100.79 and so on. It goes to infinitely many digits. But we want to round that off to the nearest whole number of rabbits because populations, it doesn't make sense to say 100.79 rabbits, so we're going to say it's approximately 101 rabbits at that time. So now the other question, the last question for this example is when is a population going to be at 600? So what I'm going to do is I'm going to be solving this equation, but I don't at this time have an algebraic way of doing it. So what I'm going to do is I'm going to do it graphically. So I graph p equals 600 up here, and as long as I've done a reasonable job of my graph, I can now estimate what is the amount of time that it'll take. Now I make this statement, the root of the equation is the x-coordinate of the point of intersection, just so I'm making it clear that this equation, I'm not solving it algebraically. The way that I'm getting the root of that equation is by taking the x coordinate, or I guess I could have said the t coordinate, of the point of intersection of this graph, the curve, and this graph, the p equals 600. So I'm looking at what is that point there, and what is the x coordinate, or I guess it would have been better to call this the time coordinate. And it's about 17.72 months. Now, the question asks for you to answer to the nearest day, so you could leave the 17 months and just convert that 0.72 into the number of days if you just take that decimal portion, the 0.72 and so on, and multiply that by 30 days per month, and that'll give you approximately the number of days. So 17 months and 22 days. Now that's all great if you have a base of 2, and now we use the base of 2 because of the fact that population was doubling. But we want to consider other cases and know what to do with the base. So for example, if we had a base, if we had a situation where the population was tripling, then it makes sense to use a base of 3. If a population is growing by 10% per year, what you can do is use a base of 1.1, which is 110%. So whatever the initial population is plus 10%, that's 110%. And if the population is decreasing by 5% per year, you would subtract 5% from 100 and you get 95%. As a decimal, that's 0.95. And if you're taking the population and halving it, then you want to multiply by 1/2 repeatedly. So that concludes this lesson on characteristics of exponential functions. Thanks for watching and have a great day.